Okay, so for number 6, okay, we've got carbon, okay, which as an element is just a single, is reacting with oxygen, which as an element comes as a pair. Okay, it's one of those things we have to remember. Okay, and it's going to produce carbon dioxide. So this one's pretty easy. Okay, carbon dioxide, 1 carbon, 2 oxygens, and the reaction is already balanced. Okay, what kind of reaction is it? Synthesis, yeah, and that's the trick, right? Because carbon dioxide is one of the products, and it's one of the products in a combustion reaction. But nothing was actually, there was no hydrogen here, so it's not a hydrocarbon. Okay, but it does look that way, right? No water was produced either, okay, and water has to be produced in a combustion reaction, so we're looking at synthesis for that one. Okay, for number 7, so we've got calcium oxide, so Ca with O, right? That is ionic or molecular? It's ionic. That means I need to check my drop and swap. Calcium's a 2+, oxygen's a 2-. That already balances out, so I'm good with that. It's reacting with magnesium chloride. Magnesium's a metal, so this is also an ionic compound, so 2+. Chlorine is a -1. Not to be confused, because some people do this, okay? They look at chlorine and like, oh, it's special, it comes as a 2. But it only comes as a 2 when? By itself, okay? So we don't want to get that confused, okay? Chlorine's charge in an ionic compound is -1, okay? So I drop the 1 to here, I drop the 2 to here. It does just happen to work out that it comes out as a 2 here, but that's just because of the drop and swap. Okay, that's going to produce magnesium oxide. Okay, that's a -2, that's a +2, so that compound works out. And calcium chloride. Okay, that's a +2, chlorine's a -1, so when we drop and swap, we're looking at that. Okay, that's what our reaction should look like, all written out. Okay, what kind of reaction is that? It's a double replacement reaction. Ionic compound plus ionic compound is always going to be a double replacement reaction, and it's already balanced. Okay, how many people have done number 8? Okay. So we got hydrogen iodide. If hydrogen is listed first, it's behaving as a what? Metal. Okay, so that means this is an ionic compound. Iodine's -1, hydrogen's +1, so that's already dropped and swapped correctly. Okay, it's reacting with oxygen, O2, okay, and it's going to produce iodine. Anything I have to do with iodine? It's special, right? Comes as a 2, okay, and water. Okay, now I wrote it as H2O. Why did I do that instead of HOH? Yeah, that's how it's in order. There's no OHs anywhere in here, so it doesn't make any sense for me to write it that way. It's easier to track where the oxygen and the hydrogen come from if I write it that way. Okay, so now I got to balance this whole thing. There's lots of 2's in here, but I think my best bet is to start with oxygen, okay, because it's in a smaller number with a bigger number on the other side. Okay, so 2 oxygens here, so I need to put a 2 here, which gives me 4 hydrogens. So I got to go back here and put a 4 in front of this. That gives me 4 iodine, so a 2 in front of that. Now my reaction is balanced. Okay, how many people have done number 9? Let's look at number 9. Okay, so we got magnesium, Mg. Okay, is Mg special? No, there's only one special metal. What is it? Hydrogen, yeah. Okay, and it reacts with nitrogen, which is special, to produce magnesium nitride. All right, is that going to be an ionic compound? Yes. Okay, so as soon as I know I'm making an ionic compound, I put in my charges, because I'm going to have to drop and swap. All right, so the 3 is going to go here, the 2 is going to go here, and now I've got to balance my whole reaction. Okay, the nitrogens are already balanced, so that's good. The 3 there will take care of my magnesiums. I'm done. Okay. All right. Questions on any of that? Okay. Then let's look at predicting the products of a chemical reaction. All right, so the first thing we're going to just quickly review, because we already know how to do it, is balancing. Okay, if I want to write a proper chemical equation, okay, sorry, this is lesson 14, right? Yeah, okay, in your notes package. If I want to write a proper chemical reaction or chemical equation, I need to make sure I obey the law of conservation of mass. That is, I have the same number and type of every atom on both sides, reactants and products, of the reaction. If I don't do that, then I have either created matter or destroyed matter, and I can't do that. Okay, so I always have to make sure that a reaction is balanced, and the way we do that is we just add coefficients, the big numbers, okay, in front of all of our compounds. We can't change the little numbers, obviously. They have to do with dropping and swapping and stuff like that. Okay. So if we're looking at this chemical reaction, okay, and looking at the law of conservation of mass, okay, mass must always be conserved. So in this reaction here, I start out with 4 hydrogen atoms on the reactant side, 2 oxygen atoms on the reactant side, okay, both of them in the form of molecules. So it's 1 molecule of oxygen made up of 2 atoms, 2 molecules of hydrogen made up of 2 atoms each, okay, and that's going to form water on the other side, but I still have 4 hydrogens and 2 oxygens on that side. Okay, I haven't created anything, haven't destroyed anything. I've just done what Dalton says happens in a reaction. I've rearranged everything, or in this case, I've joined the atoms together. Okay, so looking at that diagram on the right, which diagram on the right shows the correct pairing of products to reactants? Okay, so box A is my reactants. Okay, which one of these boxes shows the products? Which one? Well, all we have to do is count it up, right? So look at how many yellows we got here. 1, 2, 3, 4, 5, 6, 7, 8 yellows. Okay, there's only one of these that has 8 yellows in it, right? And that's got to be D. I think the other ones are okay for the reds, but okay, if the yellow is the only one that can possibly be showing the law of conservation of mass being obeyed is D. Okay, we have the same number of particles, okay, in D as we have in A. We obviously have way fewer in C, okay, and there's not nearly enough yellow in B, okay, for it to be conserved. Okay, everybody all right with that? So that's just, again, the reasoning behind why we balance a reaction, which we already know how to do. So if we want to balance a chemical reaction, we first write the chemical formula. You don't ever balance a word reaction. Okay, so you're never going to be given a reaction written out with all the names and say, balance this. You don't ever balance a word reaction. You only ever balance a reaction in formula form. So I write out the chemical formula for each reactant and each product. You don't have to include the state of matter for us, but when you get to Chem 20, that will be an expectation. Okay, for step 2, try balancing the atom or ion present in the greatest number, unless it's what kind of reaction? Combustion. Combustion has its own set of rules. Okay, so use coefficients. That's numbers that go in front of each element or compound to get equal numbers of atoms on both sides. Repeat step 2 to balance all the rest of the stuff. Okay, and then when you're done, double check. Okay, once in a while you'll get a situation where you think you've balanced it and you walk away from it, but one of the numbers you wrote messed up something and you need to go back and fix it. Okay, so always double check a reaction when you think you have finished balancing it. Okay, so I want to have a look at this reaction here. I'm just going to write it out kind of by itself here. Nitrate. Okay, so we've got copper reacting with silver nitrate. Okay, and that's going to form silver and copper 2 nitrate. Okay, so what should I start balancing here? What's present in the largest number? No?
The 2.
Yeah, nitrate is present in the largest number. Okay, now some people would tell you you need to balance each and every atom by itself, which you can do. Okay, and if this nitrate were for to some reason break up into nitrogen and oxygen separately, you would have to do it that way. Okay, but looking at this reaction, I can see nitrate stays together. Okay, the nitrogens and the oxygens are not separating, so I can balance it like I would chlorine or any other element. Okay, so on this side, there are 2 nitrates. So I'm going to go over here. There's only how many nitrates here? 1. Okay, so I'm going to put a 2 in front of this to make my nitrates work. When I do that, it gives me how many silver? 2. Okay, and there's 1 copper over here and 1 copper over here. That was my double check, by the way. Okay, so we said when you think you're done, double check. Okay, well, the copper works, the silver works, okay, and the nitrates work as well. Okay, so looking at this reaction, what do I produce in this reaction? What's Ag stand for? Silver. So I take copper and I react it with silver nitrate, which is a solution, and I get silver, solid silver. Would that be useful?
If you want to make silver.
If you want to make silver, which is far more valuable than copper is. Okay. Now, are you actually making silver? No. Okay. You had it to start with. Okay. Lots of times when people look at this, they're like, Mr. Coder, do we have any of that stuff? Because they're thinking, I'm going to get rich. I'm just going to pour this stuff in a bottle and stick some copper wire in there, and I'm going to have silver the next day. And they're right. They would. That's actually how this reaction goes. Okay. Used to be like when we actually had pennies, okay, they had enough copper in them that you could throw them in a solution of silver nitrate and leave them for a couple of days. When you came back, the penny would be plated with silver. Okay, so it would look like you had a silver penny, okay, and then you could actually just flake the silver, okay, right off of it afterwards. Problem is, silver nitrate contains silver, and it's thus really expensive. Okay, you're not actually getting ahead here. Okay, you think that you can just buy some silver nitrate and then make silver. Okay, it doesn't work that way. Silver nitrate contains silver and is thus very expensive. Okay, all right, everybody all right with how we balance that one? Okay, because we've been doing balancing already for a while. All right, so predicting the products of a chemical reaction is very, very similar to what you've already been doing. Okay? On every reaction question you've had from me so far, you've been asked to identify the type of reaction. That is the first step in predicting the products of a chemical reaction. Okay? So when you're being asked to predict the products, all you're going to get are the reactants, like you see for these ones here. Okay? Can I tell what reaction type is going on with just the reactants? Yes. We only went over 5 types of reactions. They all start differently. Okay? So looking at number 1, I've got an element reacting with another element. What's the only reaction that starts that way? Okay. So there's our first step. We've identified this as a synthesis reaction. Now I have to understand what happens in my reaction types. What happens in a synthesis reaction? 2 elements, right, combine, and they form a single compound. What kind of compound is going to be formed when I put a metal with a non-metal? An ionic compound. All right, so in an ionic compound, I write the metal first and the non-metal second. Okay, what do I have to do with all ionic compounds? Drop and swap. Okay, so this is a -2, this is a +2, so that compound is okay the way I wrote it. All right, I've written out my reaction. What do I have to do with it? Balance it. Okay, so I've got 2 oxygens over here. Now I have 2 oxygens over here. Okay, that gives me 2 calciums, so I got to go back over here and make sure I have 2 calciums. Okay, is that a whole lot different than what we were doing? Not really. Okay, I mean, yeah, you had to figure out what the products would be, but you're just following a pattern. Okay, so instead of me actually just giving you the products, now you have to write them out yourself. Okay, but it only involves you being able, or having to be able to identify the reaction type and understand the pattern. Okay, so what kind of reaction is going on in number 2? It's decomposition. We only have one reaction type that has a single reactant. The only thing that can happen if you only have one reactant is for that reactant to break down. There's nothing for it to react with. Okay? So this is a decomposition reaction. Okay, so that's step one. Okay, what happens in a decomposition reaction? They separate, right? They become elements, separate elements. So the two elements that will be separated here are magnesium and sulfur. Anytime I make single elements, what should I check for? If any of them are special. Is magnesium special? No. Is sulfur?
Yes.
Yes. Okay. Am I ready to balance now? Yep. Okay, so I got 8 sulfur over there, 8 sulfur here. That makes 8 magnesiums. 8 magnesiums. Let's balance. So all you really have to do, or all you really have to know, is the patterns involved in our 5 reaction types. What happens in each one? Okay, what kind of reaction is going on in number 3? Okay, now for combustion, it's easy. What are always the products of a combustion reaction? CO2 and water. You just have to remember that. Okay, there's nothing to figure out here. The products of any combustion reaction are carbon dioxide and water. All that changes is how much of each. Okay, do I need both balancing rules for this one? Nope. Okay, 3 carbons, 8 hydrogens, 8 hydrogens, okay, 4 oxygens plus 6 oxygens is 10. 5 times 2 is 10. What kind of reaction are we looking at in number 4? It's double replacement. We got 2 ionic compounds. Okay, in a double replacement reaction, all that happens is the metals switch partners. Okay, so we just need to make 2 new ionic compounds. Okay, so that'll mean that H, who does H end up with? OH. And sodium ends up with? Chlorine. Okay. Is it balanced? 1 hydrogen, 1 hydrogen, 1 chlorine, 1 chlorine, 1 sodium, 1 sodium, 1 OH, 1 OH. Looks balanced to me. Okay. That's all there is to it, guys. Identify the type, use the pattern to figure out who goes with who, balance the reaction. Okay? Occasionally, you'll have to look for special elements and drop and swap your ionic compounds. Okay? I didn't show you dropping and swapping these, but this is a -1, that's a +1, +1, -1, so they were already good, okay, on the drop and swap. Okay. So, I'll maybe give you a copy of this flowchart. You don't really need it, okay? It's kind of the steps that we went through. Okay? What I want you guys to do is try those ones, okay? So write them out and give them a try. See if you can predict the products of those reactions there. Okay, so for number 5, I've got beryllium reacting with iodine. Okay, so both of them are elements. So what kind of reaction are we looking at? This is a synthesis reaction. All right, so in a synthesis reaction, okay, the pattern is that the 2 elements will combine to form a single compound. All right, so that means that beryllium will end up with iodine. Now, that's an ionic compound because this is a metal, so that means I need to drop and swap. Okay, and that's always something I need to look for. If I make an ionic compound as one of my products, I need to double check that it's dropped and swapped. If I don't, I won't be able to make my equation balance correctly. Okay, so iodine's a -1, beryllium is a +2, okay, so 1, 2. All right, so now I've got my product written correctly. Now I need to balance the reaction. Done. Okay, because it's already balanced. Questions on number 5? Okay, let's look at number 6. So in number 6, I've got potassium, a metal, an element, okay, by itself, reacting with iron 2 oxide. Now, how do I know it's iron 2?
Because oxygen
Exactly, because iron has a -2 charge. If this was a double replacement reaction, that would be important, because I would need to know that when I drop and swap iron with whoever it ends up with on the other side. In this reaction, it's not as important because iron's going to end up alone. Okay, so that means iron's going to be alone, and potassium is going to end up with oxygen. Okay, is that going to be an ionic compound? Yes, so I need to drop and swap it. This is a -2, this is a +1, K2O. Okay, so this is what I was talking about a couple of days ago when I said you really need to have your formula writing and name writing down in order to do the reaction stuff, because now you're being asked to do it all the time. Okay, in fact, to generate these compounds by yourself. Okay, so now that I've got everything written out and I know I've dropped and swapped everything, I should probably check and make sure that any of the elements that were produced were special. Is iron special? No. Okay, so it doesn't need a number beside it. Now I can balance the whole reaction. The only thing that's out of balance right now is potassium, and a 2 here will fix that. All right, how many people have done number 7? Well, let's have a look at 7 and then I'll give you a little bit more time here. Okay, so for number 7, I've got copper 2 sulfate. Is it important to know that it's copper 2?
Yes.
Yes, it is. Okay, how do I know it's copper 2? Because sulfate is a -2, and there's one of each of these. That means that this is the copper with the 2+ charge. So that's going to be important on the other side, because this is a double replacement reaction where copper is going to switch places with magnesium. Okay, so who does copper end up with on this side? Chlorine. And magnesium is going to end up with sulfate. All right, those are both ionic compounds that now need to be dropped and swapped. I figured out who goes with who, but now I need to figure out the numbers. So I figured out a minute ago that this is the copper with the 2+ charge. Chlorine is a -1, so this will be CuCl2. And then magnesium is a 2+, and sulfate's a -2, so that compound is okay the way I've written it and doesn't need any brackets. All right. Now what do I do? Balance. Okay. So, looks good. Already balanced. Okay. There's 1 copper here, 1 copper there. 2 chlorines, 2 chlorines. 1 magnesium, 1 magnesium. 1 sulfate, 1 sulfate. Okay. So we're good on that. All right. I'll give you a few more minutes here, guys. I want you to try 8, 9, and 10. Okay, so for number 8, I've got a compound that contains carbon and hydrogen, and it's reacting with oxygen. What kind of reaction is that? It's a combustion reaction, and the products of a combustion reaction are always the same. They are always carbon dioxide and water. Okay, so now that I've got that, okay, now I need to balance. Do I need both balancing rules? Got an even number, okay, so I'm going to start with a 2. All right, 2 times 4 is 8. Now I got 8 carbons on both sides. 2 times 10 is 20. 10 times 2 is 20 on that side. And now I can work on the oxygens. 10 oxygens in the water, another 16 in the carbon dioxide for a total of 26. 13 times 2 is 26. Okay, so combustion reactions, the only real trick with them is the balancing part. The products are always CO2 and water. All right, what kind of reaction am I looking at for number 9 with only 1 reactant? Decomposition. All right, so I got a decomposition reaction. I'm going to break this compound up into its 2 elements. That would be rubidium and phosphorus. Okay, anytime I produce single elements, what do I check for? Special elements. All right, do I have any? Yes, phosphorus is special, comes as a 4. Rubidium is not, so I don't have to put anything beside it. Now I need to balance the reaction. So what should I do first? Yeah, get the phosphorus done here because it's the biggest number. Okay, so 4 on that side, 4 on this side now. 4 times 3 is 12. I got 12 rubidium, and the whole reaction is balanced. All right. And then for number 10. So on number 10, there's a couple of tricks we have to watch for here. Okay? What kind of reaction is it first up? Okay, it's a double replacement reaction between two ionic compounds. So we know right off the bat that all we're going to do here for the products is switch the partners on the metals. So that means that lead is going to end up with phosphate, and cobalt is going to end up with chlorine. All right, but there's a bit of a trick here. Both of these metals have more than one possible charge. I can't do the drop and swap over here on the reactants, or sorry, on the product side until I have figured out what charge I'm supposed to use from the reactant side. Okay, so lead's got more than one charge. It can be a 2 or a 4. Looking at this compound, which one is it, 2 or 4? It's a 4, because chlorine's always a -1, and there's 4 chlorines. So this is the lead with the 4+ charge. Phosphate is a -3. Okay, so I'm going to drop and swap. A 3 is going to go here. Brackets are going to go around the phosphate with a 4 outside of the brackets. Okay, got to do the same thing with cobalt. Phosphate is a -3. That means I have a total of 6 negative charges. Okay, I have to get 6 positive charges from these, so each one is a +2. So now when I go back over here, I know that this is cobalt 2 chloride. So when I drop and swap, that's what that one's going to look like. Okay, that's about as tricky as they get for a double replacement reaction. Because really all there is to a double replacement is swapping the metals. Okay, then you just got to check for special charges. All right, now that I've done that, now I can balance the whole reaction, and I would say I probably want to start with phosphate. It's the biggest number. Okay, so there's 4 phosphates on the product side. Now there are 4 phosphates on this side, which gives me 6 cobalts. I'm going to go over here and make sure I have 6 cobalts. That gives me 12 chlorines. So I go back over here and make sure I have 12 chlorines. This is a good sign. That gives me 3 leads. I got 3 lead over there. Okay, now I know the whole reaction is backwards. All right, questions on that one? So the 2 toughest reactions that you're going to run into are the 2 replacement reactions, single and double. Okay, double because you could have lots of this weird charge stuff. Single replacement because you're always going to produce an element that you have to check to see if it's special, and an ionic compound that you're going to have to drop and swap. Okay, so those are the 2 that are usually going to give you the most trouble. All right, we'll leave it there for today. Okay, we'll be working on that again tomorrow. Okay, if I can get everybody to mask up, I'll come around and spray down your desks. If you can wipe them off, please.